Swayam Prabha. Digital India. Educated India.
So we have these definitions for pursuing the idea of regime diagram for premix turbulent flames. Of course, in this process we have assumed somewhere along here that the Schmidt number equals 1. So let us suppose that for scaling purposes take the turbulent dissipation as V prime cube divided by the integral length scale. Could only show typically that it is of the order of, but let us suppose that we take it is equal to, then putting things together, essentially what you are looking for is an expression for V prime over SL in terms of non-dimensional quantities. So the non-dimensional quantities actually what we are looking for is expressions for V prime over SL in terms of L over LF with the non-dimensional quantities involved in there, and we should now be able to show that this is equal to RE times L over LF to the minus 1 and that is also equal to Karlovitz to the 2/3 divided by times L times L over LF time to the 1/3. Why are we doing this? Because that is what the regime diagram is all about. The regime diagram is one on V prime over SL on the vertical axis plotted against L over LF. What this basically means is that when you want to talk about turbulence, you talk about it in by characterizing in two ways. One, what are the length scales involved in the turbulent flow that we are talking about. The other one, what is the intensity that is involved. Okay, so these are two things. Essentially, it's sort of like in a time signal kind of thing. What you are talking about is what are the frequencies involved and what are the amplitudes involved, right. So these two things essentially indicate that, and in both the cases and for both the parameters, what you are looking for is to compare these two with their corresponding flame related quantities. That means we are saying, can we now look at the turbulent length scales in comparison with the flame length scale, like the flame thickness, right. So are we having typical eddy sizes that are bigger than or smaller than the flame thickness, right. That is on the one side as far as the scales is concerned, and as far as the intensity is concerned, when you now have a flame that is trying to propagate at a particular speed, if the flow that is out there is now fluctuating, right, at a certain intensity, if the fluctuation is very small, that as the flame is beginning to propagate, it does not really go through any jitter. It just this is so small that the flame can just go through without even realizing that it went through a fluctuation, right. Then you do not really have a turbulent flow at all. Or in other words, if you now had significant amount of intensity, that means the amplitudes are very large, right, then the flame is going to now go through fluctuations correspondingly. Therefore, how are these fluctuations, the fluctuation in turbulent fluctuation intensity, how is it comparable to the flame speed itself, right. So these are the two things by which we want to compare, characterize this. So we will now have values thrown in on a log plot. This is actually a logarithmic diagram. So we will now look at 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, etc. Or maybe just one more space for 10 to the 4, and similarly over here could actually look for something like a squarish picture, 10 to the minus 1, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and so on. Okay. And what we want to point out here is the relationship between V prime over SL and L over LF through Reynolds number is one of a inverse relationship, right? That is, this goes as 1 over that, and with a Reynolds number as a coefficient, and therefore we would actually like for a normal plot, it should actually be like a rectangular hyperbola that's forming the relationship between V prime over SL to L over LF for constant Reynolds number, but this is actually a log-log plot. So in a log-log plot, this actually shows up as a negative, a straight line with a negative slope. And in this particular exercise, what we are trying to do is to have, for example, in this case, this involves like the Zeldovich scaling, and we're using a Zeldovich number value of about 10, and that's something that we have seen long ago when we are trying to scale the premix flame thickness to find out how much is the reaction zone thickness going to be relative to the preheat zone thickness. And so correspondingly we now expect that a Reynolds number of 1, a constant Reynolds number of 1 line is going to be a straight line in the log-log plot with a slope that is inclined downward for R equals 1, and this regime now is essentially what we call as laminar flame. That means with the turbulent Reynolds number defined this way, this line corresponds to R equals 1. Anything greater than R equals 1 forms this region to the right of and above of this line, and anything that is to the left of and bottom below this line is laminar, right? So that means for turbulent flames we are essentially interested in all of this regime. That is point number 1. Then the next thing that we have to look for is how is V prime over SL related to L over LF through Karlovitz number. So can we now plot constant Karlovitz number lines, and the answer is this is actually going as 1/3 of that, and therefore in a log-log plot it's going to be a straight line with a slope of 1 over 3, alright, and the line is going to go upwards. So we start doing this at this point corresponding to 1 over here, and now draw a line that is Ka equal to 1 and Karlovitz equal to 1. We now start from this point. So we now have this entire turbulent combustion regime at the moment divided into 2 parts, right? One which is having a Karlovitz number less than 1, and another one that where the Karlovitz number greater than 1, and in both the cases the Reynolds number is greater than 1. Within this regime we now want to further differentiate between well, you could use actually a straight line, a continuous straight line. This is a horizontal line. This is a horizontal line corresponding to V prime over SL equal to 1. That means V prime equal to SL, right? So this is a regime where RE greater than 1, K less than 1, but V prime is greater than SL. This is a regime where RE is greater than 1, Ka less than 1, and V prime is also less than SL, right? And finally we want to now look at the situation where the second Karlovitz number is greater than 1, right? So we now have a boundary, and that is also going to go the same way, because Karlovitz number, this is basically delta squared Karlovitz, right? So they are directly related. So V prime over SL in terms of Karlovitz delta, Ka delta, is going to also have a 1/3 relationship for the L over LF, alright, with simply a different coefficient delta squared. Therefore you will have the same slope, but then it starts at around 10 because we are looking at a Zeldovich scaling of 10, and so I mean these things could be a little bit off this way, that way, okay, but essentially we are getting the picture like this depending upon the value of your Zeldovich number, and this line corresponds to Ka delta equal to 1. Therefore this is Re, therefore you now go back and say Re greater than 1, Karlovitz greater than 1, but Karlovitz delta less than 1, and here we now have Re greater than 1, Ka greater than 1, Ka delta, let us just use this space, Ka delta greater than 1. So that means we now have 4 regimes that we have marked. One based on Karlovitz less than 1 but V prime greater than or less than SL, okay, we have got 2, and when Karlovitz is greater than 1 we still have Karlovitz delta less than or greater than 1. So that is how we are splitting this. So what is the significance of doing it this way? The answer is we are now going to now call this the wrinkle flamelet regime, and we are going to call this the corrugated flamelet regime. We are going to call this thin reaction zone regime, or reaction sheet regime, you can call it either way. So you can say thin reaction zone or reaction sheet regime, and this is what you would call as broken flamelets regime, or the well stirred reactor regime. It's differently called in different textbooks in this way. Well, so that's kind of interesting. So just to make it a little clearer, we could probably use like a different color chalk piece for this is the 4 lines that we're talking about that demarcate these 5 regions, and so why are we, the question is why are we calling these what they are, right? So now let's think about what happens in each of these cases. So the first one is the wrinkle flamelet regime, and here we are having situation of Re greater than 1, Ka less than 1, and V prime less than SL. So when we say Ka is less than 1, and look at what is Ka. Ka is essentially the flame time to the Kolmogorov time, alright. So essentially it's comparing the flame scales with the Kolmogorov scales, or essentially what it basically says is we are still looking at the flame to be significantly thinner than the turbulent scales, right. So that's what it basically means. So you now have a flame that's, let us say, marked by 2 lines. We will try to do this for quite some time, and then the point essentially is we will be able to do this for quite some time, and that's what I would like to impart here. These 2 lines are essentially this line is like the reaction zone, the thickness, including the thickness of the reaction zone, and the dotted line is actually the upstream edge of the preheat zone. So the preheat zone is spanning the thickness corresponding to this distance between these 2 lines, and the thickness of this continuous line itself represents the reaction zone, right. So effectively in a one dimensional flame you would have the reaction zone, and upstream of it you will have the preheat zone. So the upstream edge of the preheat zone is what is marked by this broken line, but we are now showing it as curved because what we are basically saying is this is now interacting with an eddy that is going around like this. So its tangential velocity is Vn depending upon the eddy size, and this flame is now propagating locally normal to itself with a flame speed SL, right. And since you are having a situation where V prime is still less than SL, the intensities are significant to make the turbulence felt by the flame, unlike in a laminar flow, but still not enough to penetrate the flame or do anything more. All it does is to basically make the flame wrinkle around the eddy, right. The flame is too thin, and then so the whole of the flame is too thin, okay. We will now progressively get to the point where the eddy sizes are smaller when compared to the flame thickness, or the flame is becoming thicker when compared to the eddy sizes, whichever way, right, and then things are going to get a little bit more complicated. So the next regime, for example, would be the corrugated flamelet regime, where the Reynolds number is greater than 1, alright, the Karlovitz number is still less than 1, alright, but V prime is greater than SL. So this means the intensity is now larger than the flame speed, so the eddies are now going to make their presence felt on the flame a lot more. So what this basically means is the velocity here is going to be large, and correspondingly the flame has to give way. So that's how the flame always tries to do things, right. It now, when the flow is locally large, it gives way by inclining itself to the flow such that only a component of the flow direction is balanced by the flame speed, right. So what then happens when this now begins to increase is, so if you now think about a eddy that's now having a larger Vn, and you now have a flame that is interacting with it, it now actually begins to curl up to encompass that. So which means in fact you could exaggerate this a little bit more by saying, strictly speaking, you could say that means the corrugation in the flame can now house an eddy comfortably, right. Previously we didn't have the flame corrugated so much, but now you have a corrugation of the order of the eddy size, right. So that's the reason why it's called a corrugated flame. Then we now get into the thin reaction zone, or the reaction sheet regime. So here Re is greater than 1 and Karlovitz is also greater than 1, and of course V prime is greater than SL. We have long passed, we have gone past that long back, right, and therefore what we are talking about is Karlovitz is greater than 1, and that means the turbulence scales are now bigger than the turbulent. Look at this. If Karlovitz is greater than 1, then the flame thickness is now getting to be bigger than the turbulent scales, right. So what that really means is you're now going to have a flame that is having a preheat zone starting out like that, but you now have an eddy that is big enough to penetrate the preheat zone, and then the preheat zone thickens. Why does the preheat zone thicken? Is because you now have a turbulent transport of heat and mass. the job of the preheat zone is essentially transport, okay, where heat from the reaction zone is being transported upstream to the reactants and mass from the reactants is being transported downstream to the reaction zone, right. So you have a heat and mass transport that is happening in the preheat zone, which is now in addition to the molecular transport that happens because of temperature and concentration gradients, is also additionally happening because of the eddy. That means this eddy is now taking the reactants and putting it into the preheat zone for the reactions to consume and taking the heat from the preheat zone and bringing it a priori ahead to the reaction zone and heating it up, right. So if you want to think about this in a statistical manner, it's as if like you had a fairly thick preheat zone. The eddy was doing the job of thickening the preheat zone, right. So you now can only talk about a reaction zone that is now trying to give accommodate the eddy, but the preheat zone has been breached. That's essentially what's going on. So therefore that's the reason why we are calling this a reaction sheet regime. That means all that we can talk about as a characteristic of the original premix laminar flame, the remnants of it is only the reaction zone. The preheat zone is now marred, right. So effectively the way we are thinking about this is, can I hold on to my laminar knowledge, right, and that's just beginning to get breached here by the turbulence. Until then it's okay, right. And there's a reason why we have been using this this term called flamelet all the time, and there is this basic idea of what's called as laminar flamelets. That means you can now think about, in these regimes we can still continue to think about the turbulent flame or the turbulent combustion zone as being made of an ensemble of laminar flamelets, right. So locally where you have these things satisfied, you can now say it's essentially a laminar flame, but it's now interacting with an eddy and therefore it's getting curved or corrugated, wrinkled or corrugated, right. So you can continue to preserve your idea because the original local structure of a one-dimensional laminar flame, how we extended it from a one-dimensional laminar premix flame to, let's say for example, a Bunsen burner, the shoulder of the flame there, or the base of the flame there, or the tip of the flame there, in all these things we try to accommodate the one-dimensional idea. Locally the flame is trying to match the flow, right, or it's shaping itself to match the flow, and that happens everywhere still, right. So you could hold on to that. That means locally if you now look at these gradients, you can draw exactly the same pictures that you drew, that is the concentrations are now falling down, the temperature is now going up and all that stuff. That structure is there, right, but here that structure is breached, okay, except only for the reaction zone. And then finally you now get into the WSR or the broken flames. The well stirred reactor, the WSR regime, here of course the Reynolds number is greater than 1, of course the Karlovitz is greater than 1. We got to go back and point out that we still have Karlovitz delta less than 1 there for the previous case. That means the eddy sizes are still not big enough to small enough to breach into the reaction zone, but that's no longer the case here. So here we have Karlovitz delta is also greater than 1, right. So in this case what happens is even the reaction zone is torn apart. So that means you now have the flow getting into the reaction zone and coming back again, and locally it can strain the reaction zone and cause local quenching and reignition and so on. So that means you now have the flame torn apart into shreds because of these eddies, right. So this causes local quenching and reignition events. Let's now talk a little bit about non-premix combustion. So non-premix turbulent flames. I'm following Peters here, and there is more work that's been done further out in more recent past, but I'm not covering that material as far as this is concerned. Now the problem with non-premix combustion regimes is we don't have a characteristic flame speed here. Right, but instead what we want to actually look at is if you are looking for velocity gradients in the flow, and of course turbulent flames will have velocity gradients in the flow. So so if you're now looking at something like a strain rate, let's say it's given by symbol A, and you have, like, let's say something like dou infinity by dou y for the flame. It's also related to the pressure gradient in the flow, that is, like, you can say dP by dy equals rho infinity A squared, where A is the strain rate. And so if you now have a strain rate, then the strain rate actually has dimensions of time. Okay, so this is meters per second, this is meters, right? So it's, sorry, strain rate has a dimensions of 1 over time, right? So then with this we should now be able to come up with a diffusion thickness LD equal to d over A the whole to the half. So that's like meter squared per second divided by 1 over second, so the 1 over second gets cancelled, you get meter squared per half gives you meter. So now we are basically looking for something like a characteristic dimension associated with the flame in order to be able to compare with the turbulence. That's what we were doing for the premix flame. There it was rather easy to think about a time and space relationship through the flame speed, but here we didn't have a flame speed, so we are going through this. The next thing that we want to do is we don't want to actually think in terms of physical space, because in diffusion flames the mixed diffraction actually comes up as a very handy tool, and we went through this when we did diffusion flames, you see. So when you have diffusion flames, it's one thing to actually get the flame shape in physical space, but if you want to actually look at the flame structure, you are better off looking at the mixed diffraction space, because in the mixed diffraction space all the concentrations and temperatures are all related to the mixed diffraction, and if you now supply the local mixed diffraction you can find out how these things vary, right. So in the mixed diffraction space we can now have a corresponding diffusion thickness that is corresponding to the diffusion thickness that we have defined, LD. Diffusion thickness in the mixed diffraction space now is, let's suppose we call this delta ZF. Again the subscript F is corresponding to flame here, because we are looking at the diffusion thickness around the stoichiometric surface, right, because you have the flame and then you now have a certain length scale associated with the flame that the eddy wants to interact with, right. So in the mixed diffraction space it's always about the stoichiometric mixed diffraction where the flame is. Therefore what you are saying, what we are looking for is the conversion from the physical space to the mixed diffraction space goes through the modulus of the mixed diffraction, modulus of the gradient of the mixed diffraction at stoichiometric condition times LD. And we also had the scalar dissipation rate. So scalar dissipation rate chi, we did define this, and that is twice d grad z mod squared. So obviously we can get an idea, we want to try to put these two together. So that means delta Z F, the diffusion thickness in mixed diffraction space, is chi st divided by 2a the whole to the half, right. Now if you want to just make this a bit simpler, what you can do is you can now expand chi st about chi st for small values of z and then approximate. Let's not say, or let's say the z is not varying too far out from zst, right, and then chi depends on z, therefore you expand chi about chi st for small values of z. That's like a Taylor series approach. So expanding chi of z for small values of z about chi st, and when you say small values of z, that means we are approximating, so we can show that delta z of is approximately 2 zt, right. So this is effectively the counterpart of LF in premixed flames, right, and should basically point out that this is mostly the preheat zone. And we did point this out when we were doing diffusion flames, if you recall, right. So when we did the laminar diffusion flames, what we pointed out was the Burke-Schumann assumption was essentially saying that the flame is a sheet along the stoichiometric surface, but that was essentially the reaction sheet, right. So it's sort of like saying in the preheat, in the premix flame, if you now think about only the reaction zone as a sheet, but consider the thickness of the preheat zone, like the way we have been drawing pictures here, right. Then what happens in the Burke-Schumann problem? You have a flame that is a sheet which is like a reaction zone, and you do have the transport going on, that is mixing of fuel, an oxidizer and heat. All these things are going on outside of this sheet, and if you want to think about what happens to the reaction rate, the infinite reaction rate assumption is the one that says that the reaction rate is almost infinite here, but if you now try to zoom in and then clarify this reaction zone like we would do in the premix flame, then we would find that it's essentially the reaction rate that is going to be peaking only at this sheet, similar to how we did in premix flames, right. So effectively in most of these we have been mainly interested, up to here we have been mainly interested in the premixed flame regime diagram, what's the preheat zone doing relative to the eddies, right. So similarly, if you are now thinking about a corresponding diffusion thickness for the flame, we should be worried about this in the mixed diffraction space, this which is this, how is that going to actually interact with the eddies, and that is like the counterpart of mostly the preheat zone of the premixed flame. And here again the laminar ideas are coming back to help us. Now the reaction zone thickness, on the other hand, right, so this is the one where you have the fuel and oxidizer consumption zones, right, and we would like to point out that the oxidizer consumption zone is actually quite larger in reality. That is what we are saying is, if you now do actual chemistry, right, the detailed chemistry for, let's say, methane air flames or something, what you should find is the oxidizer significantly leaks out of the reaction zone to a farther distance outside, into the fuel region. Okay, so keep that in mind, and we would like to now call this delta ZR. This is the counterpart of L delta that we had in the preheat zone, in the premix flame, sorry, and we would now like to relate this to epsilon delta ZF. That means it's a fraction of the diffusion thickness. Now, what we know from literature on detailed kinetics, like or diffusion flames with detailed kinetics, is, so we'll just take this empirically here. So it is seen that so let's just call what we wrote here as delta Z epsilon. Delta Z epsilon is going with respect to chi st power 1/4. This is actually from 4-step methane air chemistry calculation. And then we try to relate the epsilon here to the extinction epsilon. So by scaling epsilon with epsilon q at extinction, then we can show that epsilon over epsilon q is chi st divided by chi q to the 1/4, and therefore can just write here delta ZR divided by delta Z F is epsilon q chi st divided by chi q to the 1/4. Now, the reason why we want to do this is actually the one that gives you L delta divided by L. That's a counterpart in the premix flames that we saw, which is what is the length scale corresponding to only the reaction zone thickness, L delta divided by LF, where so as I said, this is the counterpart of LF, and that's this, and this is the counterpart of L delta, okay, from preheat zones. So we're kind of doing something very similar here as what we did for the preheat zone, so premix flames. So what we want to plot here is a fluctuation amplitude Z prime divided by the diffusion thickness in mixed diffraction space, and on the right hand side, on the x axis or the horizontal axis, we want to plot something as a measure of turbulence, which is now going to be the scalar dissipation rate at extinction divided by scalar dissipation rate at stoichiometric. Now, strictly speaking, we got to actually average this to indicate a forward average. In fact, this is what's called as a conditional forward average. Scalar dissipation rate. Let's not worry about what it exactly means. For the moment, we will simply take it as of the same order as the scalar dissipation rate at stoichiometric condition. And in fact I should also point out what is meant by this z prime. So z prime is nothing but z what's called a z double prime squared tilde to the half. Double prime essentially indicates a forward averaged fluctuation. So this is essentially a forward RMS. Okay, so it's a root mean square of the forward averaged fluctuation. Okay, so that's what it means. And similarly, when you now say z prime st, what we really mean is the root mean square forward averaged fluctuations obtained at the stoichiometric condition. Right. Now if you're so now let's put some numbers here. So we can say 1 or 10 to the 0 or 10 to the 1, 10 to the 2, etc. there, and then let's say, so this is 10 to the minus 1. We'll start with 10 to the minus 2 on the y axis, 10 to the minus 1, 10 to the 0, 10 and 10 squared and so on. And what we should be interested in is a region that's greater than chi q by chi st greater than 1, because when you now have a region that is less than 1, this is the extinction chi. So essentially this corresponds to flame extinction, right? And then what we should be interested in is when you have actually we should show this so we have z prime st divided by delta zf going as chi q over chi st. You can see that here. You have a this is opposite, so you have a minus 1 over 4 in a log scale. So starting from here you now go through a line that is like this. So this is z prime, in fact you should say zst divided by delta zr equal to 1, and this is slope minus 1 over 4. We are taking chi st tilde as approximately same as chi st here, as I said. And then you also have one more situation where you're looking at similar to previously, where we had u prime was comparable to SL and zst prime is comparable to delta S. So that's here. So this is zst prime equal to delta zf. So that now breaks up things into 4 parts. One is so the flame extinction is one region, then we have what's called a separated flames, connected flames, and connected reaction zones. Right, so let's again explain these things. So when you now have for example zst greater than delta f, right? Now what this means is you now have fluctuations that are actually greater than the delta zf, and delta zf is actually corresponding to like the preheat zone, and this basically means that fluctuations are or extending to sufficiently lean and rich sides, and therefore what this means is that you are now taking some amount of, so that the fluctuations are now causing some amount of lean side of the flame to go to the rich side and vice versa. So this actually begins to now separate the flames, because the flames are effectively dictated by the what's near the stoichiometric surface for the reaction zone, and if now you have these things going on, you will now create intermediate regions of stoichiometric surfaces, so the original flame is essentially broken. So this begins to cause separated flames, so causes the reaction zone to get separated. Now for ZST less than delta ZF, right, we do have intense mixing, but not enough to cause separation, and sometimes you can also get partial premixing. So what this means is you can have the reaction zone move around without really getting disconnected, but you will now have the preheat zone sense the fluctuations. So effectively then you don't really have disconnected reaction zones. So this is essentially connected flames, that is reaction zones are connected, and finally for ZST less than delta ZR, this is now beginning to look like fluctuations are still smaller than the reaction zone thickness itself. Then even the reaction zones, I should say here, reaction zones are disconnected, but here even the are connected. Now what it turns out is actually you can sense these things completely in a jet diffusion flame. So if you now think about a jet diffusion flame along its axis, then the jet diffusion flame axis actually goes through these different regimes as you go along this and come down along here. So you can now see these different regimes exist in a jet diffusion flame corresponding to this. We'll stop here and pick up from here on some other day.